Okay, so we want to know where standard electrode potentials come from. So you have a chart that shows them. And so on this chart, basically what you have is you have a whole bunch of different chemicals. And you have a symbol that looks like an E with a knot, and then it has brackets that says volts. Okay. And essentially how you use that is you find the difference between the two voltages listed on that sheet, and you will then know what the potential should be for a voltaic cell made up of two of those half cells put together. Okay, so we want to know, how do we get standard electrode potentials? For half cells. Okay, so let's start with something that we're probably a little familiar with by now, and that is with like a copper zinc scenario. Okay, so let's look at a voltaic cell to begin with and think about what we would expect to happen in this particular voltaic cell. So you might have a beaker here. It's not quite a straight beaker. And then you'd have one nearby. Okay, and within these beakers you're going to end up with strips of metal. Okay, and we know from past experience that these metals have different abilities to reduce each other. Yes. So in this case, let's say that we're dealing with two metals, and we'll say that on this side we have zinc, and on this side we have copper. So the first thing we want to know is which way is the reduction going to tend to happen. Actually, I guess before we do that, we need to put these into electrolytic solution. This solution should contain zinc ions, and this solution should contain copper ions. Okay. I don't know how important it is what the anion in the solution is. I don't know if it really matters that much. We were using copper sulfate and I believe zinc nitrate. Okay. We're then gonna, we could test it by actually hooking up some sort of resistor on here like a bulb, and we would notice that it would glow. Okay. What's more often done is you're going to test the voltage across each of these. So you'd have to break this here, right? And you put your voltmeter right in here, and you can test the voltage. Okay. If there's no voltmeter and you complete, actually, if you hooked it up like this, would anything happen at this point? What's missing from this scenario? Right. So you need something that bridges between these two containers. So usually that's like a tube filled with a liquid. Usually there's like a cotton ball jammed in the end so that the liquid can't escape, but that ions can pass through. And this is quite often something like potassium nitrate solution. And as the current flows, right, there's going to be a reduction in oxidation. And what that'll do is it'll tend to change the balance of charge within the solution. So the salt bridge is there to replace those ions that are lost so you don't get an off balance of solution. So if you look at your chart, which of these two metals has is more active or more reactive? So look and see. It's higher on the list. Copper is. Are you looking here? Zinc is about, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, about 8 or 9 metals more active than copper. So which way, right or left, are the electrons going to tend to travel in this cell? Do they go this way? Yeah, that's right. We're going to have electron flow going in this direction. Okay? So what does that mean? Okay, so what that means is zinc here, since it's pushing electrons away, is going to take on, it seems a little counterintuitive, but it's going to take on a very slightly positive charge, okay? Slightly positive charge. So that means that cations are going to be repelled and anions are going to be attracted to it. So let's say the anions are something like nitrate. Because of this slightly positive charge here, these nitrate anions are going to be attracted towards here, and they're going to lose electrons into this solution. Sorry, that's not right. My bad. My bad. My bad. Sorry. Sorry. That's not what's going to happen. What's actually going to happen is zinc metal is going to come into solution. That's what's going to happen as zinc 2 plus. So it's going to donate the electrons that are traveling around this loop, and then zinc ions are going to enter the solution. So what is going to happen over time is that the anode is going to start to corrode away. Okay. So why is it an anode? It's an anode because it attracts anions. Does that make sense? You have to know that. Okay. Over on the other side, we have the arrival of electrons, and copper metal is going to start to be pulled out of solution or deposited out of solution, and these electrons come and they neutralize the charge on the ion here, and we get copper metal depositing onto cathode. Why is it the cathode? It's the cathode because cations are attracted to it. So here's our electrolytic cell. Now the question is, what voltage would we measure here? And in order to do that, what we're going to do is we're going to look at our table of potentials, half cell potentials, and we're going to find zinc on here. Oh yeah, there it is. Okay, zinc is negative 0.76 volts, and copper is 0.34 volts. Okay, so essentially what you're going to do is you're going to find the difference between these two values, and that's going to be the voltage of the overall system. So V net is, or I guess delta V or V net is 1 minus A. I guess it doesn't really matter which way you go. One way would be considered positive, and one way would be considered negative. What I'm really interested in is the difference between the two. Does that make sense? So what will we get here? 1.1, right? So we should be able to generate 1.1 volts off of this cell. In one direction, it's considered negative, and in the other, it's considered positive. Just going to pause this for a second. So the question is, how do we get these values in the first place? Okay, you can find tables of these things, and so where do they come from? And one little note here, okay? These are designated as E naught values. Okay, they're the half cell potentials. So let's figure out what the story is on a half cell potential. Okay, so there's a standard half cell that all others are measured by. Okay, and that's the hydrogen half cell. And one thing to note, the solution is 1 molar, okay, and these readings are taken at STP. Okay, so it's standard temperature and pressure. So 1 atmosphere, I believe 273 K, and 0 degrees Celsius. But I'm going to double check on that. Okay, so just a little correction. It's not normal STP. It's electrode standard, which is 25 degrees Celsius, okay, and 1 molar solution, and 101.5 GPa. So this is 298 Kelvin. Okay. So does that really matter? Not really. Okay. But this is what those standards come from. So what's a hydrogen half cell? Well, a hydrogen half cell looks like this. It's, oh my, hard to draw a straight line on this thing. So what does it look like? It looks like this. So we've got container. Okay, and inside this container, you have a solution, and it's got an acid in it, so it's got H+, so it could be, I guess, probably whatever acid you want, and at a concentration of 1 molar, okay, or 1 mole per cubic decimeter of water. And into that, you're going to invert a test tube. Test tube. Okay. This is a special test tube. And this test tube kind of looks like this. And it's got a inlet here. And it's got an electrode here. Like that. And into here, you're going to pump hydrogen gas. Okay? So this electrode inside of here is made of a non-reactive metal. So it's platinum. Platinum electrode inside there. And you pump H2 gas in, right? So this is surrounded by hydrogen gas. It's passing over it and coming near the surface. Okay, so the reaction, depending on which way you go, is either to strip electrons off of hydrogen and add more acid, or it's to push electrons onto H+, right, and reduce H+ back to hydrogen. So depending on what you attach it to, you either get electrons flowing this way, or you get electrons flowing that way. So for instance, let's say we want to know the half-cell potential of let's do lithium, okay, because it's the far end of the spectrum. So what we would do is we would take a lithium half-cell, okay, we would make a solution here, which contains some lithium ion. To be honest, I don't know exactly how this is done, because lithium would tend to want to react with water. There's got to be some way to do this. Let's do one that's not as hard to understand. Let's do aluminum. Okay, we'll switch it to aluminum, because I actually don't know how you would get lithium. There must be another way, because you can't just put it in water, right? But aluminum you can, so we'll go with that. So let's say this is an aluminum strip. Got some Al water. If you look at your chart, okay, does aluminum reduce hydrogen, or is aluminum reduced by hydrogen? And we also would have to have our salt bridge here. Okay. So this is the setup to test aluminum, right? Now what you'd do is you'd put your voltmeter on here and you test the voltage between the two. Okay. But which way would we tend to go? In other words, who's the anode and who's the cathode here? If you look and see, which one's the stronger reducing agent? Is aluminum the stronger reducing agent, or is hydrogen the stronger reducing agent, yeah, aluminum is. Okay, good. So what's going to happen then is electrons are going to be pushed this way onto here, and hydrogen is going to be reduced at the platinum electrode. Okay. If we were to say take something that is less reducing than hydrogen, like say copper, then you'd have the electrons flowing in the opposite direction. So what you do is you go through and you test, and you'd find out that for this particular scenario you get a negative 1.66 volt. Okay, negative 1.66 volt. So electrons are traveling onto hydrogen at negative 1.66 volts. Now you'd go through and you test all your metals, and then you have a standard, and this is considered to have a half-cell potential of what do you think? It's the standard by which all others are 0, right? This is considered to have 0.0 volts, okay? So away you go. Is this practical to ever use in an actual like voltaic cell? Probably not. You got to supply gas, you got to set up this outrageous scenario. But what it does do is it allows you a standard by which to measure out all the other metals, right? And therefore you can figure out, if you know the difference between it and hydrogen, and the other metal and hydrogen, you can find out what the voltaic cell's voltage will be overall. Does that make sense? Okay. One more thing